Hi, everyone. This is Anurag Pandey, and I'm your instructor for CE 321. And today I'm going to talk a little bit about safety planning and safety estimation. And I'm going to go ahead and share my screen. Okay, give me 1 second here. Let me go ahead and share my screen again. Share. And I'll stop my video. So this is chapter 6 of your textbook, Pricker and Whitford. It's specified in the syllabus. And first of all, I want to talk a little bit about how this safety discussion is different than what you might have learned in when you applied Ashto Green Book formulas about what should be the radius of the curve, for example, or for safety, we want to provide a certain radius on the curve. You don't want the curve to be too sharp. So that's also sort of safety discussion. And then also about thinking about what is the safe stopping sight distance and all of those things. And obviously those are driven by safety discussion as well. But what we are going to talk about here is slightly different than the safety issues that you learned about when you're looking at applying the design standards. So the key difference there is between what we call the nominal safety versus substantive safety. The nominal safety is an absolute that's represented by blue curve on this line. So if you look at the blue line on this chart, that's basically what represents a substantive safety. And I'm sorry, the nominal safety. The idea is that if you are above a certain threshold, like for example, if you provide a radius of certain type, of certain level, a certain number of larger radius, then you make the curve safe. If you provide appropriate super elevation, then you make the curve safe. And then that's when you sort of are looking at your low risk environment, your crash risk goes down. But then if you don't provide those, then you're at higher risk. And that's sort of a step function. So either you're safe with low crash risk or you're unsafe. But in reality, if you think about safety substantively, that's not how it always works. Even if, and most of our roads are designed to standards, but that does not mean that they're not going to have any crashes. Under certain circumstances, there would actually be crashes that are going to happen, even if your design is perfectly safe by what the Green Book, Ashto Green Book prescribes, or its California equivalent, like for example, California Highway Design Manual, is prescribing to you. If you do those design, even then there are going to be some collisions or crashes on the road. And one thing, a side note I want to note here is that I use the term crash here, C-R-A-S-H, I should probably revise the spelling here, but crash risk. And I don't want to use the term accident, because if you think about what accident entails, accident makes it sound like you're talking about some act of God. While if you say crashes or collisions, that means that, as a safety engineer, as a transportation engineer, you could do something about crashes or collision. If it's a completely an accident, it's just a matter of chance. It was going to happen anyway, right? So because we think crashes are preventable, so the right term to use as a transportation engineer, or even as a general public, and I try to correct all the media organizations if I see them using the term accident to correct that and say it's crash or collision, right? So that's one side note I wanted to mention, that anytime you're talking about things that lead to fatalities and injuries on the road, let's call them collisions or crashes and not accidents. So, and then to make my other point is that, yes, so what you've learned about from Ashto Green Book or MUTCD, Manual for Uniform Traffic Control Devices, all of those guiding documents prescribe that you provide a nominally safe infrastructure. That means you have a radius above a certain level, you have a stopping sight distance available at all locations, and you have the decision sight distance wherever it's applicable, and all of those things. And all of those things make the infrastructure nominally safe. But nominally safe infrastructure does not mean that you're not going to have any crashes. You're still going to end up with some crashes. And that means that uh, your number of crashes are going to be sort of a continuous function of your design dimensions, your lane width, your radius of curve, your stopping sight distance, and all that. It's not going to be just a step function like that. Okay? So, and how do we estimate the nominal safety? We estimate that using some type of regression models. Typically, they are developed using negative binomial regression equations. And you learn about those stuff in CE 526, which is the class on transportation safety. It's a graduate level class that you could take if you're interested in pursuing traffic safety as a career. Factors affecting highway crashes. There is actually typically more than one causal factor that's involved in highway safety, in causing collisions. It's the vehicle capability. Sometimes there is a failure on the vehicle's part. There's a tire that goes suddenly flat, or there's some brake failure of some kind. Then there is the driver behavior. Sometimes the drivers are not paying attention to the road, so that could also be the case. And then sometimes there is highway environment. For example, even if you provide nominally safe infrastructure with stopping sight distance and all of that, but suddenly there's a snowstorm in place, or there is a dense fog that comes in. All of those things could make the highway environment unsafe. So there is figure 6.3 of your textbook that provides a Venn diagram that depicts those causal factors. So I would like you to refer to that. And again, your textbook is the Fricker and Whitford, and all these section numbers and figure numbers refer to the 2015 edition of the textbook. In terms of planning, Federal Highway Administration, FHWA, stands for Federal Highway Administration. That sort of is the governing body for highway infrastructure in this country, in the US. And they have a highway safety improvement program outlined in and that sort of talks about planning, implementation of improvements, and then evaluation of improvements effectiveness. And it sort of describes the Highway Safety Improvement Program, HSIP, as sort of a cyclical process. So you plan, and in the planning phase, you collect and maintain pertinent data. And pertinent data would include all the collisions data, but then also include all the design data, what type of roadway design exists, what's the roadway width, lane width, and so forth, what's the ADT. So all of those are pertinent data. ADT would be average annual daily traffic, what type of vehicle traffic is crossing that road or crossing that roadway location. And based on that data, we identify hazardous locations. And again, how do we do that? You learn that process in transportation safety class. And then we conduct engineering studies. And then we establish where we want to make those improvements. And there is this idea of, how do we make systemic improvements to safety rather than just sort of chasing our tail with kind of creating specific spots. And all of that you learn in CE 526, which is a transportation safety class. But here, what I want you to know is that safety planning, implementation of improvements, and then evaluation of improvements effectiveness is a cyclical process. And it involves all of these steps of collecting the data, analyzing the data, and then based on that, identifying where we want to do the improvement. And specifically how we identify those sites, that process that we should be looking at systemic point of view, and you learn that process in CE 526. So this is a graphical or a flowchart based depiction of the same process. Planning component, there's this implementation component and the evaluation component, and then it becomes sort of a cyclical process. Like, once you've done the evaluation, you go back to another improvement process, or you sort of go back to the planning process and relook at the data, the new data that might have come in post-improvement, post-evaluation. And as I said, this is a cyclical process, so you go back and forth between these steps. Now, in terms of identifying hazardous elements of the road, this is page 310 to 311 of your textbook. Again, this is the 2015 edition of the Fricker and Whitford textbook that I'm referring to. But how do we, so one thing that is important is thinking about crashes and normalizing them into some kind of a rate of crashes. Because frequency of crashes, for example, you might have a roadway location with very low AADT, very low average annual daily traffic, very few cars and bicyclists and pedestrians pass through a certain location. And that location, even a few number of crashes mean that that location is unsafe. But as opposed to like a major arterial where there's a lot of traffic. So for example, what I'm trying to say here is that 5 collisions at location A may not be the same thing as 5 collisions on location B. That you have to normalize those locations by how much exposure to traffic those locations have. And that exposure, the normalizing by exposure, is what we do when we're trying to compute crash rates. So how do we compute crash rates? There are 2 different formulas. One is for intersection location where 2 or more roadways are meeting. And that for locations, that formula is defined as RMEV, which is rate per million entering vehicles. So RMEV stands for rate per million entering vehicles. And that is obtained by crashes per year, okay, divided by the approach ADT. So approach ADT basically from all 4 approaches. For example, I'm going to go ahead and draw an intersection here for you. So I'm going to go ahead and draw. So if I'm drawing an intersection here, so I'm going to do that drawing. So let's say if this is an intersection, and I want to draw this same thing. This is an intersection. And once I draw an intersection, what I want to look for is I want to look for entering traffic on all of these locations. So for example, in this location, whatever number of cars are coming in from here, 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 and here. So I add the entering volume of traffic, ADT, average daily traffic, from all 4 of these approaches. And that tells me how much traffic is approaching this roadway intersection. And I add those up, and that's what gives me the approach to ADT. Days per year, we always take it as 365. And then this is number of crashes per year. And then because we have this million entering vehicle, we multiply that by 10 raised to the power 6 to get what is our entering rate. Now, on a roadway segment, the formula works somewhat differently. For example, for roadway section that are not within 100 feet, that's the standard definition that we use. Yeah, if you're trying to define a crash rate for a location, you want to find a location that's at least 100 feet away from intersection, any intersection, and then based on that, you figure out what is the rate per million vehicle miles. RMVM is the formula for that. So if I'm trying to figure out what is the crash rate for a roadway section as opposed to an intersection, so what I'm trying to look for then is that I'm trying to draw a roadway location, and this might be a segment that's like, maybe I'm looking at a 1 mile segment of this road. I'm looking for a segment between this point and this point of the road, and this might have like sort of 2-way traffic. So I might be looking at 2-way traffic on the road here. Okay, so I'm looking at both ways, and then that basically gives me the ADT of the segment. And then when I'm trying to analyze the segment, I'm interested in, as I said, remember the units are rate per million vehicle miles. So I'm interested in the length of the segment. So this length of the segment also comes into play. And I'm trying to, so what's the length of this segment? I'm trying to measure that length in miles. If it's a short segment, I'll enter that in feet and divide that by 50 to 80 to do a miles conversion. And then I'll obviously have number of crashes that happen on this segment on both directions. And then divide that by approach ADT days per year. We always take that as 365. And then this 10 raised to the power 6 is estimated to convert that into million vehicle miles. So you can see that I define the rate for intersections differently than for roadway sections. But the idea is to normalize by how many vehicles are actually trying to use that roadway facility, be that an intersection or a roadway segment, before we can compute the rate. And that gives us more apples to apples comparison between what locations are more hazardous, are experiencing more than expected number of crashes versus those that are expecting fewer number of crashes. Because we typically expect more crashes to happen at locations where there is higher traffic coming in. And this sort of, whenever we're just trying to rely on rates, one thing to note there is that we are assuming that there is a linear relationship between exposure to traffic and number of crashes. And that relationship does hold for a certain period of time or certain amount of exposure, but that may not always be the case. So you have to be careful. But I think and again, that discussion, we have that in our CE 526 transportation safety class. But since we're talking about this in an introductory transportation engineering class, for now, just knowing the definition of the rates, and then also knowing just in back of your mind that because the relationship between number of crashes and how much exposure to traffic a site has may not always be linear. So there are some limitations to that. Just knowing that there are limitations that exist when we're trying to identify hazardous locations just based on crash rates, just knowing those limitations exist, and then how to compute the crash rate would be sufficient for now. But again, if you become a traffic safety professional, we do need to figure out what are those limitations that come from relationship between collision numbers and exposure not being linear. What are the implications of that? Again, we learned those implications in our transportation safety class in CE 526. So clear all drawings. Again, this is a problem here because we don't want to say accident. We always want to say that in terms of crashes. So I left that over here because I did want to, so that we want to always use the term crash and not accident. Even if still you see, you still see older literature that uses the term accident, we always want to correct that. So same thing, I'm gonna do that here as well. So I don't want to use the term accident here. I want to use the term crashes rather than accident. So I'll make sure that we always I wanted to highlight that here again, that this is not the right term we want to use. But so how we want to look for crash patterns, we sometimes do expected value analysis, which compares local crash rate to expected rate for similar facilities, plus 2 standard deviations. So we look at, like, for example, if you're interested in finding out which of the two-way stop control intersection locations are more hazardous in our county, we look at sort of more suburban counties in the state, we look at two-way stop control intersection, all of them, and then we figure out what is the average collision rate at two-way stop control intersections, and then we sort of figure out the standard deviation of that. And then in our county, we look for locations that have experienced average plus 2 standard deviation more crashes. So that tells me that certain number of locations are experiencing way higher number of crashes. So if there is a location that is experiencing the average crash rate plus 2 standard deviations of crashes, that means that location is really typically more hazardous, considered to be more hazardous, and we want to probably apply some countermeasures. Now, if you take a systemic approach, we just don't want to fix that intersection. In fact, what we try to do is that we kind of see whichever intersections fall in that category, what do they all have in common, right? And then we try to fix that issue at all of those locations. In fact, we treat anyway, if there are other locations that have same characteristics, even though they don't have crash rate quite as high as those locations, we try to fix that issue systemically. Again, we just had the discussion, in our transport safety class. But for now, I hope you realize expected value analysis means finding the average crash rate, finding the standard deviation. So figure out what is the average plus 2 standard deviation, and try to identify locations that have higher than that crash rate. And then for cluster analysis, we look for unusually large group of crashes with common characteristics. And cluster analysis can really help us figure out, for example, which locations are having more sort of left turn related crashes or T-bone type crashes at an intersection. And if you have those, then possibly those T-bone type crashes can be treated at an intersection. Maybe roundabout might potentially be a solution, because now instead of having T-bone type crashes, you're going to expect like more merging related crashes when you convert a two-way stop control intersection to a roundabout. So cluster analysis can also help us when you look at unusual grouping of crashes with common characteristics, then also can tell us a little bit more about, how do we treat those crashes? Okay, so that's another important thing to know. Okay. Next slide. Go ahead and clear all these annotations. Factors considered in cluster analysis, those would be your crash type, so your severity, whether it's a rear end crash, side swipe crash, that's just describing how the collision is happening between two vehicles. Severity, whether it's a fatal crash that led to a fatality, whether there's an injury crash, or whether there's just a property damage, what are the contributing factors, visibility restriction, traffic control, driving impairment, whether there were any environmental factors or certain time periods of the day. Maybe there is a lot of crashes that are happening during nighttime, or during Friday or Saturday night, where you expect people to be more people to be driving intoxicated, things like that. So we look at all of these, and again, I want to spotlight here and say that we don't want to use the term accident, we want to use the term crash type and not the accident type. So this is sort of an example collision diagram that you might see when you're trying to look at an intersection, for example. So this, again, as I was saying, as a safety professional, this is pretty old data. This is a collision diagram from year 1975. So this is a 1-year collision diagram from January 1st, 1975 to 31st December 1975. So this is a collision diagram. This location experienced 15 total crashes. And again, because, so the 1975 was the time when we were still using the term accident. You find that term being used quite a bit. So I left that information here, but I want to keep highlighting that we don't want to use this term accident. We still want to use just crashes. Okay. But reading, in terms of the reading of the collision diagram, you could see the legends. The symbol means moving vehicle, and then all of these different type of crashes have different legends. If there's a head-on crash, this is how it's depicted. A side swipe crash is depicted this way. So you can see type of collisions. You can see head-on, side swipe, out of control type crashes, left turn crashes, right angle crashes, all of these. Time, day, and date. So you can see time, day, and date. Weather and road condition, that's your number 2. Night, wet weather crashes, snow related crashes, and then if there's nothing, that means it's clear. And then night, if between dusk and dawn, so if it's a nighttime crash, then they specify that. So this collision diagram can convey a lot of information about what type of crashes are happening. And then you will see that there are total 15 crashes that are denoted in this figure. And so for example, you could see there was this backing vehicle type crash that happened. There was a fatal crash. So anytime there is a fatal crash, and again, we want to use the term crash here. An injury crash is depicted here. That's out of the 15, there are 3 that involved a fatality or an injury. And then if there is, so I see that these were the sort of the 3 injury crashes. I don't see any fatal crashes because fatal crashes are depicted by a closed circle here, but with unfilled circle represents an injury crash. So you could see. So that's how you sort of interpret a collision diagram, and this is based on the collision data that might be out there. And then implication due to human factors, and this is sort of what makes transportation engineering so different than structural engineering, because you could have everything by design, but because of human factors, you might still have collision. So there is that ergonomics or engineering psychology. Sometimes there is some ideas around, if the drivers feel that they can, like, for example, if you design, for example, you want the freeway lane to be wide enough so that drivers can drive at the desired speed. For example, 70 miles an hour design speed, you want to provide a 12 feet lane. But if you sort of take that same philosophy of making the drivers comfortable and you apply those to a city street, even if you might have a lower posted speed limit, if the drivers see a wide 12 feet lane, excuse me, they will try to drive fast, and that might not fit your goals for safety, for example, right? So there is this ergonomics or engineering psychology that has implications for safety. And then that's why, you want to, what safety means on a freeway facility where you expect and want the drivers to be going as fast as possible, that might have adverse safety implications when you try to apply those same philosophy on city streets. And that's why you have to kind of think about how drivers are going to interact with, or road users are going to interact with your infrastructure. There's perception reaction time that could be different for different drivers, although we sort of use the 85th percentile information around that. What is the 85th percentile reaction time? And we use some of those conservative values for those. But again, because certain drivers who potentially might be older drivers or might be intoxicated drivers, they might have a slower reaction time. And those, those things can affect and lead to collisions on the road. And then MUTCD, which is the Manual for Uniform Traffic Control Devices. And how do you design those traffic control devices? And what are the design prescriptions you should have? All of those depend on the human factors quite a bit. So how we universally have traffic signals to be red light, right? So stop means red light always means stop, right? And why do we have posted speed limit to be always in white signs that is enforceable speed limit, and the regulatory speed limit is always in the white signs? Because we want to have our traffic control devices to be consistent so that the drivers are not confused by it, right? So human factors is what drives all those things. So for example, we always want to have advisory signs in yellow so that they are easily visible to all drivers. That's basically based on MUTCD has those regulations that the signs have to be certain size and they have to have certain consistency between them. All of that is because of human factors. So human factors play a big role in how we design for safety. Okay, so with that, I'm going to conclude this chapter on traffic safety and how do we sort of plan for traffic safety. What are some of the implications? So from this, I want you to be able to compute the collision rate or crash rate. I want you to always use the term crashes or collisions to refer to accidents. So there are no accidents on the road. What happens on the road that leads to injuries and fatalities, those are collisions or crashes, not accidents. And then you should be able to kind of read a collision diagram for me, and then figure out how many crashes are happening, which of those crashes, based on the legends provided with the collision diagram, you should be able to read a collision diagram for a roadway segment or for intersection location. So I hope you enjoyed this lecture. Thank you very much.